Good afternoon and welcome to video 3 in our quick tour of linear algebra. Today's topics, what are we going to talk about today? We're going to talk about basis or bases. We're also going to talk about dimension. Helps to know how to spell. Dimension. And also linear dependence. Okay? And here's how I want to start it off. We'll talk about our friend R2 here. We've seen that before. And I want to talk about some special vectors here. And one vector I want to talk about is that vector right there. And the other vector I want to talk about is that one right there. So again, if we were drawing these vectors, okay, one of them would go this way, and the other one would go right up there like that. And in fact, I want to give these a name. I'm going to call this vector over here, I'm going to call it E1. And this one over here, I'm going to call it E2. And these are kind of standard names for these things. And here's what I want you to appreciate. I want to come over here to some vector. Let's pick this vector right there. So that's 1, 2, 3, 4, 1, 2. Like that. And I want to say that, well, 4, 2 is really equal to 4 times the vector E1 plus 2 times the vector E2. And in fact, I think you're willing to believe that any vector that I pick out of R2, any vector AB, like that, that's just equal to A times the E1 vector plus B times the E2 vector. Now, what we're going to say over here is we're going to say that the set, and remember these are vectors, so we draw arrows over them. These form a base for R2. And what does that mean? It means a couple of things. It means, first of all, any vector V contained in R2 can be expressed as a linear combination of E1 and an E2. Okay, and we've seen that right over here. This is any arbitrary vector out of R2, and we have expressed it as a linear combination. Now, what does it mean when we say linear combination? Okay, well, notice over here, A and B are real numbers. What wouldn't be a linear combination is as if it was something like this: A squared E1 plus B cubed E2. This is not linear. Linear implies that these have an exponent of 1. And that's a very important thing. So to be a base, okay, for the vector space means, first of all, that any vector can be expressed as a linear combination. And the second thing, let me just save this file. and it is saved. So that's number one. Number two, there is no smaller set that can express any vector as a linear combination. In other words, the thing to note here is note that this set E1, E2, there are exactly two vectors in it. There's no smaller set that could express any vector as a linear combination. For example, just consider E1. Well, first of all, E1 times any scalar R, this is just going to equal R0, like that. So I could never express any vector that had anything over in this position over here that wasn't 0. Okay, so there's one more definition that we can sort of throw in here. Definition. We say that the dimension, I'll write it in capital letters, the dimension of a vector space is equal to the size of the base. So R2 has a base of two vectors in it. Okay, so the dimension, and we would sometimes write it this way, we would just say the dimension of R2 is equal to 2. And it shouldn't surprise you that the dimension of R3 is equal to 3, and I think you can carry this on for higher dimensions. Okay, but there are a few other things that we need to say here. I want you to consider the following. Suppose we were to come over here, oops, and let me draw some coordinate axes. And I want you to consider some other vectors here. So suppose I had a vector here like this, and that's 1, 3. And let's come over here and, oh, I'm sorry, that's not 1, 3. That is 3, 1. And let's have this vector over here, which is 1, 2. Okay. Now, I want you to pick out any old arbitrary point in here. Let's pick this point right over here. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 9, 1. Now, I claim that 9, 1, and I'm thinking of this as a vector, can be written as a linear combination, some R times 1, 2, plus some S times 3, 1. Okay, and what I'm going to do here is I'm going to multiply these. So over here, I get R, 2R, plus 3S, 1S, is equal to 9, 1. And if I go ahead and try and solve this, I get that 9 is equal to R plus 3S. And then I come over here and I get that 1 is equal to 2R plus S. Well, first of all, from this one right over here, I can get that 1 minus 2R is equal to s. And now I can come back and substitute that in there. So I get 9 is equal to r plus 3 times s. So that's going to be 3 times 1 minus 2r. And that's equal to r plus 3 minus 6r. So first of all, r, that's a minus 5r. I'll put it over on this side, and that's 5r. And then I'll come over here and I'll subtract 9. So that's 5r is equal to minus 6. And that r is equal to minus 6 over 5. If I come over here and substitute that back into here, or why don't I substitute it right in here, I get that 1 minus 2 times r, well that's minus 6, 5, is equal to s. And you can see over here that's going to be 1 plus, and that's going to be 12/5 is equal to s. So 17 over 5 is equal to s. And what I've done over here is I've expressed this vector here as a linear combination of these two right over here. So the point that I'm trying to make is that there isn't a unique base for any vector space. There are, in fact, many, many different bases for it. And what we've shown over here is that 1, 2 and 3, 1 can also be used to generate any vector in the vector space R2. The point here is that bases are not unique. And that is a very, very important point. Okay, we're going to return to dimensions and stuff like that in a moment. There is something else here that's very important that we will discuss right now, and it's this notion of what's called linear, and I'm going to call it dependence slash independence. Okay? And what I want you to think about is the following, and we talked about this briefly, that if we were looking at R2, and let's suppose we considered the vector 1, 1, and let's consider the vector 2, 2. Now, the question is does 1, 1 and 2, 2 form a base? And the answer is no. I think you can see that with these two vectors that if I went A times 1, 1 plus B times 2, 2, that all this is going to do is this is going to give me A plus 2B, A plus 2B. And again, notice that the x and y coordinates are the same. It's only going to generate things on this line right here. This is not a basis for R2. And the other thing to notice here, very simple, is that if I come over here, if I go 2 times 1, 1, that's actually equal to 2, 2. So what's going on here is we say that these two vectors are linearly dependent. Okay? Well, what would it mean for them to be linearly independent? Suppose I have a vector v and I have a vector w, and they're linearly independent. Well, that's actually, there are a couple of ways that you could define this. One would say that if you were looking for real numbers r and s, if I were to go r times v, plus S times W, and I would set that equal to 0, the 0 vector, I should say. The only solution is R equals 0 and S equals 0. So I want you to think about that for a second, and let's come over here and consider the following. So for example, suppose I were to come over here and look at E1, which is equal to 1, 0. And let's look at E2, which is equal to 0, 1. And let's ask the following. Suppose I were going R times E1 plus S times E2. And suppose I told you that that's equal to the 0 vector. And I say solve for R and S. Well, that's going to say R times E1, that's just R0. And S times E2 is going to give me 0S. And when I add these two together, that's just equal to RS. And if that's the equal 0, 0, the only solution for this would be R is equal to 0 and S is equal to 0. Okay? So that means these two here are linearly independent. Okay? But what if I were to do this? Suppose I were to look at E1, comma, E2, and I also considered the vector 1, 3. Now, what would it mean for them to be linearly independent? Well, now I'm looking for three numbers. I'm looking for R, S, and T, and I want to go that R, E1, plus S times E2, plus T times 1, 3 is equal to 0, 0. And let's go ahead and solve this, or see if we can solve it. Well, this over here is going to be R0, and this is going to be 0S, and this is going to be T, 3T is equal to 0, 0. So from here, I get that R plus T is equal to 0. R plus 0 plus T, and then I get 0 plus S plus 3T. I get S plus 3T equals 0. Well, from the first thing, I get that R is equal to minus T. And then over here, if I, well, okay, so R is equal to minus T. And then if I come over here and I get that S is equal to minus 3T. Okay, so what does that mean? Well, if you think about it, that says that there are, in fact, lots of solutions to this over here. Okay, so for example, if T is equal to 1, then I'm going to let R equal minus 1. And if T is equal to 1, then S is equal to minus 3. There's a solution. Okay, suppose I were to let T equal 2. Then I could come over here and I could say, well, R is equal to minus 2 and S is equal to minus 6. That's another solution. Okay, so what this means is that these three vectors right here are not linearly independent. Okay, we know that E1 and E2 are, but we know that when I add this third vector over here, okay, this is not linearly independent. Okay, there's a linear dependency that exists between them. So the conclusion is here is that these three vectors don't form a basis for R2, but we saw that E1 and E2 does. So what we can do here, let me just save this. Okay? Recall again that the dimension of a vector space is equal to the number of vectors contained in the base. Okay, and recall again that the base has two properties. One, it can generate any vector in the vector space, as a linear combination. And the other thing about the base, its size is minimal. That's a very key point. And that, my friends, is the end of this section.